So hello everyone, today we will be discussing about Whitney's inequalities. Okay, we have theorem 4.4 for every graph G. The kappa of G is less than or equal to lambda of G, which is also less than or equal to delta of G. So first let's know who are these three. Okay, let's note kappa of G is the vertex connectivity, so it is the minimum number of vertices that need to be removed to disconnect the graph or make it trivial. Second, we have, so this one is the vertex. Second, we have the lambda of G, which is the edge connectivity. That means it is the minimum number of edges that need to be removed to disconnect the graph. So if this one, we will remove vertex or vertices. Here, we will remove the edges to make a disconnected graph. And lastly, we have the delta of G, which is the minimum degree or the smallest degree among all vertices in a graph G. Okay, let's have this one as our first example. We have G here with vertex from A to I. And now let's identify the value of the kappa of G, lambda of G, and delta of G. Okay, so first the kappa of G. So what is the minimum number of vertices na ato ang kwaon para ma-disconnect ang graph? So in this graph, in this example, it is very clear that we can use vertex E. Vertex E to disconnect a graph, which means we just need only one vertex para ma-disconnect ang graph, because if we will B, then getting B will not disconnect the graph, will not directly disconnect the graph and any other vertices here. So the value of our kappa of G is 1. And now let's get the value of our lambda of G. So it is the minimum edge para ma-disconnect ang graph. Okay, so here we have, let's try to get this one. If we will remove other edges, let's say this one and this one, the graph is not disconnected. Okay, let's find one edge to disconnect the graph, because one edge is the minimum edge na maka-disconnect sa graph. But here, we can find just only one edge na maka-disconnect sa graph. So let's have two. Okay, let's try this one and this one, so it's still connected. And if we have this one, so the graph is already disconnected. We have this graph and this graph, so that's just two edges. Okay, so we can have the lambda of G is equal to 2. So other than that, we can also have this one, this or this, but get this one black, so it's just the same. And now let's have the delta of G. So what is the minimum, the smallest degree, what vertex has the smallest degree among all other vertices? Okay, let's have A is equal to 3. We have E1, E2, and E3, while B we have also 3. So C is also 3, 3, and E is 4. So just the same, for F to I is equal to 3. And we have the maximum for largest degree is E, but we need to find the smallest degree, and it is 3. So here, there we satisfy the theorem, which is this one. Of G, we have K of G is equal to 1, which is less than or equal to gamma of G equal to 2, and less than or equal to delta of G, which is equal to 3. So 1 is less than 2, no, less than 3. Okay. Now let's try another graph. How about if let's have a path graph. Path graph P5. P5, 1, 2, 3, 4, 5. So our kappa of G here, the minimum number of vertex na to ang i-remove para ma-disconnect ang graph is just only need 1. And can have this one, and we can have two components, which is the trivial and this one. Also, we can use this one, but not the first and the last, because the graph will not be disconnected. So okay, let's just have this one. So we have P2 and P2. Okay, so our kappa of G is just equal to 1. And what is the minimum vertex edge na to ang kwaon to disconnect the graph? Okay, we can have this one, just 1, and we have the trivial and the other connected graph. So that's the minimum. Now it's just 1. And what is the vertex that what is the smallest degree of a vertex in this graph? P5. So also 1, which is the first and the last. So here we have K of J is equal to lambda of G, which is also equal to delta of G. Okay, so now let's prove why this inequality is true. So proof states that we already observed in 4.1 that lambda of G is less than or equal delta of G, and so it remains to show that this one. Okay, but first let's clear why this one is already true based on 4.1. Okay, so that is this one. So based on observation 4.1, which says that the edge connectivity which is the lambda of G is at most, or it means not more than, the minimum degree. Not more than. So have here. This is because if we consider a vertex V, okay, let's have a graph. And this one. Here. Okay, so if we consider a vertex V with the minimum degree, which is this one, here suppose, 1, here 2, and 3. That's the number of the degree of the vertices. The minimum degree, which is the V1, removing all edges incident to V would isolate V. So if we remove this one, so we already have two components, which is this one and the isolated vertex V, and disconnect the graph. So we have the disconnected graph. Therefore, at most, the minimum degree or at most the delta of G edges are needed to disconnect the graph. So this one is already true. Okay, now we are left with this one. The kappa of G is less than or equal to the lambda of G. Okay, let's have example. If G is this type. Okay, suppose we have this one G equal to so our kappa of G is equal to 0 because the graph is already disconnected, and also our lambda of G is also 0 because it is already disconnected, so we don't need to remove any edge that will disconnect the graph given the graph is already disconnected. Okay, suppose we have G is connected, okay, complete, so that is also connected. G is complete. Suppose we have K5. Excuse my graph. Okay, so complete. Our K of G is equal to lambda of G. So I have this one. Why? Because removing just one edges will not disconnect the graph. Okay, still connected here, this one and this one. Thus, our K of G is equal to n minus 1, where n is the number of the vertices. We have 5 because this is P5, so minus 1 is equal to 4. Thus, we remove 4 vertices. Okay, here we have the lambda of G. Okay, so by removing just one vertex, one edge does not disconnect the graph. So we need to remove 4 edges to disconnect the graph, and where we have 2 components. One is a trivial and this one. So this is K5. Okay. Yes, we have also this one. And since the graph is complete for our delta of G, then we also have n minus 1, because every vertex is connected to all the vertices in a complete graph except for itself. Thus, we have also n over 1. And we have this. Satisfy that this one is less than or equal, or just equal. Okay. Let's assume that G is connected but not complete. I think we can just have it. Okay. Suppose this is not complete, and let's remove this one. Okay, this graph is connected and but not complete. So we have here that of G is less than or equal n minus 2. Remove this vertex and this vertex. So K5 have a 5 as n minus 2 is equal to 3. Thus we obtain this one in proof, which is already done here, and this one in over 2. Okay, so now let's continue to dig why the kappa of G is less than or equal to lambda of G. It's because this one is the vertex connectivity and this one is the edge connectivity. So this is the minimum number of vertices that need to be removed para maka-disconnect the graph. And since by removing this one, a set of edges can also disconnect the graph. Okay, so all this one. Okay, yeah, so by removing, what's the minimum here? Oh. Okay, suppose that one. By removing just one vertex, this one will also remove the edges. So the graph is disconnected. So each of which would also remove its incident edges can only make it easier to disconnect a graph. Okay, and since every edge cut has endpoints or vertices associated with the edges being removed, so it is generally much easier para maka-disconnect the graph by just removing edges than by removing vertices alone. So yeah, to make a graph disconnected, it's the edges that connects the graph. Okay, so if we let x be the minimum edge cut with cardinality of x is equal to lambda of g, because it is the minimum edge cut, or to make the graph disconnected, then there exists a set of vertices whose removal can disconnect the graph with fewer removals than our lambda of g. Therefore, this one is true. This one. Since we already proved that this one is checked based on the observation from 4.1, thus, and also this one, thus theorem 4.4 is true. Okay, just a small summary review for this one and this one. Since removing all edges from the vertex with the smallest degree is enough to disconnect the graph. Smallest degree, and this one is the minimum number of edge. And for this one, because it is harder to disconnect the graph by just removing vertices. It is more easier to remove edges to disconnect a graph than removing vertices. Thus, this one is 2. Okay, theorem 4.5. If G is a graph of order n and size m greater than or equal to n minus 1, then this inequality holds. The kappa of G is less than or equal to 2m over n flooring, and that means nga walay round off mahitabo even if we have this, so it's just equal to 2. Okay, so let's have proof. Since the sum of degrees of the vertices of G is 2m, it's because each edge contributes 2 to the total degree, or it just simply means that each edge connects exactly 2 vertices. So we have one edge, E1, so we can have that one. It's always this. So so the degree of V1 is 1, which is E1, and the degree of V2 is also 1, which is also E1. I think we already tackled that. Sir Sagani already discussed that one. So here the average degree of the vertices of G is 2m over n. That is 2m over n, and so this one holds. Our delta of G, the minimum degree, is less than or equal to 2m over n. So, okay, 2m over n is the average degree, and this one is the minimum degree. So, this is always true because the minimum degree is can't be greater than the average degree, given that it's a minimum. Here, since out of 3 is an integer, then this one holds. Okay, by theorem 4.4. So kappa of g is less than or equal to this one, because we have theorem 4.4, which is this one, and it was already proven. Lambda of g, and then since kappa of g, since it holds to this, of course, will holds to this one less than. Okay, let's have an example. So n minus 1, order of m, suppose we have 4 vertices, so okay, it should be connected. Okay, suppose we have that one, so this one is always, we have n is equal to 4, then this is greater than n minus 1, because n minus 1 is equal to 4 minus 1, which is 3, so that one is greater than 3. 4 is greater than 3. And okay, so for the size, so it's the number of edges in a graph. We have here 1, 2, 3. So yeah, that is the smallest we can do, because that will be equal to n minus 3, n minus 1 is equal to 4 minus 1 equal to 3, because if just have that one, so the graph is already disconnected, so that's the minimum, the equal. So m here equal to 3 equal to n minus 1. Okay, suppose we have that one, so 2m, we have 1, 2, 3 edges, so 2 times 3 over how many vertices we have? 4. 2 times 3 is equal to 6 over 4 equal to 6 divided by 4, and that is 1.5. So since it's fluorine, it's just 1, so we just need one vertex to disconnect the graph. Okay, so here kappa of g is equal to 1, which is equal to 2m over n. So theorem 4.6, for every cubic graph G, the kappa of G is equal to lambda of G. So before we proceed, let's recall what is a cubic graph. A cubic graph, or it is also called trivalent graphs, are graphs all of whose nodes have degree 3. It just means that the degree of every vertex in a cubic graph is equal to 3. So proof for a cubic graph G, it follows that kappa of G is equal to lambda of G equal to 0. So if kappa of G is equal to 0, then lambda of G is also equal to 0. It is if and only if G is disconnected. Yeah, it will be equal to 0 because, as what I have said earlier, that we don't need to choose a vertex to disconnect the graph, or a minimum vertex to disconnect the graph, where the graph is already disconnected. So both of lambda and kappa is 0. So we have here this one. If kappa of g is equal to 3, then lambda of g is also equal to 3 by theorem 4.4. So since the number of edges in each vertex is equal to 3, so we have here, this one is the maximum vertex connectivity, or we say that this is the maximum edge connectivity, because we don't need 4 vertices to disconnect a cubic graph. Ang ilang maximum degree is 3 naman, so if by removing the 3 edges, then we have 2 components, which is the isolated and the other component. So 2 cases remain, namely which is kappa of g is equal to 1 or the kappa of g is equal to 2. Since this is the maximum, so let's proceed to 1 and 2. So let u be a minimum vertex cut of g, then the cardinality of u is equal to 1 or 2, and graph g minus u is disconnected. Okay, so let g1 and g2 be 2 components of g minus u, since g is a cubic for each small u element ni u. At least one of g1 and g2 contains exactly one neighborhood of u. Let's have the case 1. So here the kappa of u is equal to the cardinality of u, which is also equal to 1. Thus, u consists of a cut vertex u of g, since some component of g minus u contains exactly one neighborhood w of u. So the edge uw is a bridge of g, and so lambda of g is equal to kappa of g is equal to 1. So okay, let's give an example to see what does it mean. Okay, for case 1, we have g equal to, let's have this graph. So we already know that a cubic graph is a graph in which every vertex has degree of 3. So here, this one 3, 3, 3, and this one. So let's connect another. Cubic is a graph where every vertex have degree 3. Okay, let's just copy here. Okay, so this graph is a cubic graph. Why? Because all vertices in this graph has degree of 3. So it states that if a kappa of g is equal to 1, then there exists a cut vertex u. Suppose this one is u. Okay, let's name the one. Q, R, S, D. Okay, there exists a cut vertex u in G. So cut vertex is a single vertex whose removal disconnect the graph. Okay, so let's remove u, which is this one. So if we remove that, okay, so we have here two components, which are this one and this one. So because G is a cubic, each vertex including u has exactly 3 edges. So therefore component G minus u must contain at least one neighborhood of u, so that is V. So in this case, any edge containing u to a component G minus u acts as a bridge. So an edge whose removal would disconnect the graph. So that's the bridge. This implies that our lambda of wait a minute. Our lambda of G is equal to 1. So this one we have 2 here and here. While our kappa of G is also equal to 1. So let's here this one is connected. So by removing u, we have also a disconnected graph. Thus, gamma of G is equal to 1, is equal to kappa of G. So case 1 is this way. Let's have case 2. Okay, if we have case 2, kappa of G is equal to the cardinality of u equal to 2. So let u equal to the set of uv. Okay, so these are the vertices that we need to remove to make a disconnected cubic graph. Assume that each of u and v has exactly one neighbor, say u prime and v prime respectively, in the same component of G minus u. So this is the case that holds if u v is an element ni edge set of G, then x is equal to the set of u prime, and v prime is an edge cut of G, and lambda of G is equal to kappa of G, which is also equal to 2. So see figure 4.3a for the situation. Okay, so u and v are not adjacent. Suppose let's have a graph example. Okay, so a cubic graph has 3 edges. So we have 2 here and 2 here. The rest is 3, the same with this graph. This one and this one. It's 2. So to make it 3, let's connect this one. Okay, let's label them Q, R, S, T, U, V, W, X. Okay, so if kappa of G is equal to 2, then there exists a set U, which is equal to the set UV of 2 vertices. We have here UV, such that removing them disconnects the graph. So here we assume each of U and V has exactly one neighbor in one component, say this one. Suppose this one is just G1 and G2. So, and 2 neighbors in the other component, say G2. Okay, so in this case, if we remove U1, U and V, then we are left with 2 components, a disconnected graph. And thus satisfy that our K of J is equal to 2. Okay, so we can say now that our kappa of G is equal to 2. So, is our lambda of G equal to 2? Yes. Just remove here, so it's already, it's also 2. Thus, kappa of G is equal to lambda of G equal to 2. So, case 2 also holds. So according to theorem 4.4, lambda of G is less than, yeah, we already have proven this one, for every graph G. So the following theorem of John Driscoll gives a sufficient condition for equality to hold in this case. So we just add this one and it's equal. For theorem 4.7, if G is a connected graph of diameter at most 2, then lambda of G is equal to delta of G. So here we have the edge connectivity and minimum degree. So at most it means that not more than 2. So the maximum diameter of this graph is 2. So before we dig to proof, let's review what is a diameter. So here we have the diameter of G is therefore the greatest distance between any 2 vertices in a graph G. So this is the greatest distance. So proof, since lambda of Kn, this is a complete graph, is equal to delta of delta of Kn for each positive integer n, and this is by theorem 4.3. So we assume the diameter of G is equal to 2. Now, if we assume, okay, let's be clear for a complete, why it's equal. Complete graph, in a complete graph, every vertex is adjacent to other vertices. So it must be this one connected, here connected, also this one. So this one is an example of K 6. So the diameter of this graph is 1 because because suppose this one A, B, C, D, E, F. So A to B is 1, A to C is also 1, A to D is 1, to E to F is also 1. The same with B, C, D, E, F. It's because it is adjacent, each vertex is adjacent to every other vertex. So here we have lambda. So their edges or their degree are all equal. So here for 6, it's n minus 1, lambda of k6 equal to n minus 1, which is equal to 5. And okay, so if we remove 5 edges, so we have here the trivial and the other component. And we have k5 and delta of k6 is also equal here 5, and this one is equal to n minus 1, which is also equal to 5. Thus delta of k6 is equal to lambda of k6 is equal to delta of k6. Okay, so now here we may assume that the diameter of G is equal to 2. So let X be an edge cut where the cardinality of X is equal to lambda of G, and let H1 and H2 be the two components of G minus X. So now let's assume that the diameter of G is 2. Okay, let's have a graph example. Okay, so since diameter of G is equal to 2, any two vertices in G are either adjacent or can be reached by a path of 2 edges. Of course, because the diameter is 2 and it is the length of a path. So A to B is 1, but A to C is 2. A to D is 1, but A to E is 2. A to F, so the diameter of A is equal to 2. The same with B, C, D, and E. So this property ensures that G is highly connected. So now let's define the edge cut. Here we let X be an edge cut of G with the cardinality of X is equal to lambda of G. So this is the edge connectivity, the minimum number of edges that need to be removed to disconnect the graph. So here X is the minimum set of edges that can be removed to disconnect the graph, because we just said that it is equal to lambda of G. So which means X has lambda of G edges. So this partition, the partition of G after we remove X, removing X from G, okay, this is results into two disconnected components. We say H1 and H2, so we'll assume that each component contains at least one vertex as G is initially connected. Okay, let's choose V1 and V2, and we let V1 be in H1, where H1 is the first component in our graph G, in V2 element H2. So since G has diameter 2, it is impossible for both V sub 1 and V sub 2 to have no neighbors in X, because that would simply imply a distance of at least 3 between them. Thus, at least one of H1 or H2 has vertices connected to edge in X. Suppose we have this one, and this one is V1, okay, and this one is V2. Okay, let's come back this one. This one is V1, this one is V2. So if this one is V1, let that one V1, because it is just a trivial vertex. Just one. So if this one, so they have a each component contains at least one vertex. So since we assume here that diameter is 2, then V1 and V2 must have been close in the original graph. This tells us that edges in X are likely to connect vertices in H1 to those in H2, since if not, then we can say it only have at most diameter of 2. So the proof assumes that each vertex in H1 this one is H1 and H2 has at least one edge in X connecting it to H2. So this is crucial because it allows us to relate the number of vertices in H1 to the size of X, and thereby to delta of G. So that's found using lambda of G. Here, our purpose is to satisfy this one. So by counting edges and applying the minimum degree condition, the proof includes that this one. Okay, here. So this one, okay. So if we erase V here, it's still connected. How about if we erase here, here, and here, it's still connected. And any vertex we remove, it will be still connected unless we get the minimum degree. So that's 3. So we have this one and this one. So by counting edges and applying the minimum degree condition, the proof concludes that lambda of G is greater than the of G, and that is in theorem 4.4. So since we know from general graph properties that okay, so we obtain here, excuse me for saying this is theorem 4.4. What I mean for theorem 4.4 is lambda of G is less than or equal to delta of G, and thus by which I don't remember if it's a property. It holds that lambda of G by these two, 1 and 2, is equal to delta of G. So then here, this one is equal. So what's the reason behind the theorem? It is that in a graph with two diameters, the connection are very close, that the edge connectivity of the lambda of G kay dili maubos than the smallest degree, which is the delta of G. Since any minimal set of edge would necessarily include at least the minimum degree to ensure this connection. So therefore, we have lambda of G is equal to delta of G holds for graphs with the structure. Theorem 4.8, let G be a graph of diameter 2 if X is a set of lambda of G, that is the edge connectivity or the minimum numbers of edges na tuang kwaon para ma-disconnect ang graph, whose removal disconnect G, and then at least one of the components G minus X is isomorphic to K1, this one K1, or this one. So let X be a minimum edge cut of G, and that is the cardinality of X is equal to lambda of G. Okay, we have the proof here. So since diameter of G is equal to 2, it follows by theorem or the previous theorem 4.7 that this one here. So furthermore, G minus X has only two components, G1 and G2. There being one, this one, because the graph is disconnected. Thus, we have two components. Since most one of V1 and V2 contains a vertex that is not incident with any edges in X. For otherwise, there are vertices X element in V1 and vertex Y element in V2, such that X and Y are not incident with any edges in X, implying that the distance of X minus Y is greater than, which is impossible a contradiction. Because we just here in our theorem diameter of 2, so that's just distance 2. Okay, so let's have an example. Here we need to satisfy this one. Okay, we have C5 and the diameter of C5 is 2. Why? Because the distance of A to B 1, but to C is 2, and to D just had to go there, so it's 2. So here 2 because it's just the same, so 2, 2, 2. And by removing minimum edge to disconnect the graph, we can have here this one. So we have two components because it is a disconnected graph, and this one is K1. Thus the theorem satisfied. This is a distance, nasa diameter 2, and ang isa niya component kay isomorphic to K sub 1 because it's at least isomorphic to K sub 1 or K sub delta of G. Okay, so I thought this was a contradiction from the theorem. If you get this 2 edge, so I don't see K1 and I was confused, but this one is K sub delta of G. The minimum degree is 2. All vertex has degree 2, so the minimum, and this one is 2. So Maybe it does not satisfy k sub 1, but it satisfies this one, so it's true. Let's have another example. Okay, this one. Suppose we have this one. So the minimum degree of graph G, for vertex in a graph G, is 2, which is this one and this one, because this one and this one, because this 4 here is a complete graph. Okay, so 2, if we remove one edge, it's still not disconnected, but if we remove 2, it's already disconnected. And here we have, just like in C5, we have here a complete, and this one is 2. So k sub delta of G is equal to 2, and we have this graph. Okay, can we satisfy both of the conditions? Is this one and this one? Yes, because it says least at least one, not at most. So let's have another example. How about this one? Okay, so here the minimum degree of the graph G is 3, because it's a complete graph for vertices. So we have n minus 1, so the number of edges in each vertex is 4 minus 1, which is 3. Okay, so if we remove just 2 edge, then it will not be disconnected, but if we remove this one, it's disconnected. And we have two components here, this one and this one, so this component is k sub 1, while this one is k sub delta of G, which is equal to 3, and this is a complete 3, this one. So thus the theorem satisfied. And lastly, we have corollary 4.9, which states if G is a graph of order n such that the degree of U plus degree of V is greater than or equal to n minus 1 for each pair U and V of a non-adjacent vertices of G, then we have this inequality. Okay, so vertex U and V is not a non-adjacent, so here we say this one, this is U and V is adjacent. So to make it a non-adjacent vertices, we put another vertex here that disconnect the vertex U and V. So given that degree of U plus degree of V, so it gives us a high level of connectivity, which means that they have a large number of connections to other vertices in G. They are almost covering all other vertices between them in terms of their connection. So just by having this one, we have the diameter or the distance of U and V is equal to 2, and that's we can relate that to the previous theorems. Here they are not connected. So by the way, this is we can use theorem 4.7 to this one. So this structural ensure that the graph's edge connectivity will match its minimum vertex degree, making this corollary true. Okay, suppose if we have a complete graph, so this will not satisfy, because in a complete graph u and v will be connected, because every vertex in a complete graph is connected to each of the vertices in a graph. Okay, example, let's have 5 vertices in which u and v will not be connected. Here u, v, w, x, and y. So u, w can be connected here also. This one, we can have a complete graph here, except connecting u and v, but other vertex can connect v. So this is like almost a complete graph. And what else? Here. Okay, we have 1, 2, 3. So because this one moro na ang iyahang adjacent, this one 4, 4, 4, and also 3 ra ang ilahang degree. Okay, so let's have degree of u is equal to 3 plus degree of v is equal to also 3 is greater than or equal to n minus 1, where n is equal to 5 minus 1. So we have 6 greater than or equal 4. So, and here this one, they are not adjacent. Okay, suppose that this one is also not connected. Let's go back. So here our delta of g is equal to, we can remove here to disconnect a graph. So we can make a disconnected graph by just removing 2 edges, because the minimum degree of a vertex is 3. So we can disconnect that one by just using 2. Here we have vertex of 3, and delta of g is equal to also 3. Thus lambda of g is equal to 3, also equal to delta of g. Thus we have here is satisfied here, and also this one, or this one, and this one.